Hi friends, today I am going to explain how to convert alternating current to direct current using the PN junction diode. So this device is called rectifiers. So to convert from AC to DC. So first I am going to start with half wave rectifier. Sir, what is the principle behind this? So under forward bias my PN junction will conduct, under reverse bias my PN junction will not conduct. So using this property I am going to solve the problem. So here what is my direct current? So my direct current, we have two states. One is on state or off state. One is either 0 state or 1 state. So we have either it will be positive maxima or minima, that's it. But in the case of alternating current, this is my direct current, but in the case of alternating current, it's a variable one. So it obeys a sine function. It's called sinusoidal wave. So it's oscillate between 0 and the positive maxima and the negative maxima with respect to omega t. Okay. So it's going to be, this is called the bidirectional current or bidirectional potential. So alternating current, bidirectional current, this is called unidirectional current. So we just want to convert this signal to this signal. So first what we are going to do here, we are going to remove the negative off cycle. So because in the case of positive direct current, we need only the positive half cycle. So we have to remove this negative off cycle. So I am going to use the PN junction diode to solve the problem. Before sending the current through the PN junction diode, we have to step down the potential. Because if in my plug point, in my socket I am getting the potential of 220 volt. If I am sending the 220 volt potential through the PN junction diode, the diode gets destroyed. So I have to reduce the potential. So I need a step down transformer to first reduce the potential, then we are going to rectifier. So first I am going to start with half wave rectifier. Half wave rectifier. So first I am going to start with transformer. So we have a step down transformer. Here we have, this is my applied potential. So this is my applied potential here. So I am going to take coil here. So that's a air core between two coils. This is my secondary coil. So this is my primary coil. This is my secondary coil. So the number of turns in the secondary coil should be less than the number of turns in the primary coil. So my NP is greater than NS. Then only it's called step down transformer. Be careful on this. So these two lines stand for the air between the two cores. So yeah, I'm going to connect this with a PN junction diode. So this is my load resistor. So I am going to get my output from X and Y. So now I am going to plot the graph for the input. So this is my input potential. Okay, input here, I am getting my output from here. So this is my output. So this is my diode. This is my point A. This is my point B. So this is my PN junction diode. So usually we are going to get the output across a load resistor. So my resistor which will prevent the other electronic device, which will resist, which will control the outflow of the output from the diode. So first I am going to plot a graph for the input. So for the input, so input is the sinusoidal wave. Okay. So next for the output. Listen carefully. In the first half cycle, this is positive, which means at point A is positive at point B is negative. The first half cycle, this with respect to point B, this is positive. So PN junction under forward bias. This is my P type, this is my N side. My P side is positive, means this is under forward bias, which will conduct, which will allow the flow of current across it. So I am getting my output across this. So here I am getting my output. So for this I am getting my output. The next half cycle, this is negative with respect to B. So this is positive, this is going to be negative. So this is negative, means my PN junction under reverse bias. When the PN junction under reverse bias, there is no conduction. So I am not getting any output from here. In the next half cycle, here I am positive. My at point A is positive with respect to B. So this is positive, means my PN junction under forward bias. Again I am getting my output. So here again it is going to be negative. Here it is a negative 1. So if it is negative 1, I am not getting any output from here. If I am not able to get any output from here, I am getting 0 here. Okay. Next half cycle I am getting my output. So I can remove the negative half cycle from here, but there is a problem, there is a discontinuity. My full waves are not rectified, only half of the waves are rectified. If the only half of the wave rectified, I cannot convert my AC to DC, because here my efficiency will be lost. The amount of current we are converting here is going to be lost. So my half wave only will rectified in this circuit. So we need a continuous one. Okay, so we need a full wave. We have to convert entire wave into output. Okay, so for that case we are going to use a full wave rectifier to solve the problem. So next I will explain the full wave rectifiers. So full wave rectifier is nothing but I am going to use the another PN junction diode here. Okay, so I will just erase this part. So I am going to do some modification here. So this then, so up to this point the same thing here. So I am going to connect the another PN junction diode here for the full wave rectifier. Next important parameter here, we have to center tap. So we are going to take a wire from the center of the transformer, the secondary of the transformer, and connect it to the ground. So this is called center tap. It's called center tapping. Okay, so this is act as my reference point. So in previous case we are taking reference point with respect to BA. Okay, what is happening A with respect to B, but in this problem we are going to take the reference point is my center tap. With respect to center tap, this is positive or negative. With respect to center tap, this is positive or negative. So I will explain. So next I am going to take one connection from here and one connection from here. So I am going to take my output. This is my X, this is my Y. So this is my input potential. Oh, sorry. So this is my input potential. This is my output X and Y. This is my load resistor. Correct. So this is my diode D1. This is my diode D2. First, what's happening? I'm going to plot the input at A. Okay. Input wave function at point A. Here. So at A or diode 1, so we have a sinusoidal wave function here. Next this is at B, so here the center tap which will split, which will invert the signal. So listen. So I am going to use this blue marker for the straight line. So when at A is positive, at point B my wave function is going to be negative. Okay. So at A is going to be a positive wave, at B is going to be a negative wave. So vice versa will change. So I am going to plot for the output. Okay. So I take this straight line here. Okay, so first what's happening? With respect to center tap, my point A is in forward bias. This is positive. So I am getting output because my A will conduct. With respect to center tap, B is negative soft cycle. Negative means reverse bias, which will not conduct. So I am getting my output from the diode 1. So I am getting my output from the diode D1. From here I am getting my output. This will not conduct. The next half cycle, this is going to be negative and my point B is going to be a positive. With respect to center tap, A is negative half cycle, which is under reverse bias. My B is a positive half cycle, is going to be under forward bias. So I am getting my output from the diode D2 or at point B. So this is going to be diode D2. The next half cycle, with respect to center tap, A is positive and B is negative. Again this is positive, this is negative. Again I am getting D1. Again this is negative half cycle. In the next half cycle, at A is negative, B is positive. Again I am getting my output from the D2. So vice versa, in every alternate cycle I am getting the output. So here my full wave is rectified, which means the negative half cycle is fully rectified. Alternating current means we have a positive as well as negative half cycle, but in the case of direct current we have only positive half cycle, which means we have only positive half cycle means there is no negative half cycle, which means the wave is fully rectified. But the problem here, my direct current, it should be from 0 to 1. There should not be any fluctuation. Here we have a AC behavior as well as DC behavior. What is my DC behavior? Only positive half cycle DC behavior. What is my AC behavior? Between 0 to 1 it fluctuates. Actually my DC should be a straight line, right? My DC should be a straight line. So here we are able to remove the negative half cycle, but we are not able to remove the fluctuation. There is a fluctuation from 0 to 1. Every half cycle there is a fluctuation. Then how can we overcome this problem? So we are going to use a filter circuit to solve the problem. So I can simply write this called the filters. Filters. So I am going to take the output from here. So instead of taking this entire diagram, I am going to take the rectifier. This is my input potential, input potential here, input potential here. So this is my XY output here. So X and Y. So we have an input and output. So this is your full wave rectifier. So again I don't want to solve this draw this entire thing. So I am going to use this. So I am getting this output at this point between X and Y. I am getting this output. So what I am going to do here, I am going to connect a capacitor and the resistor parallel to this. So I am going to connect a capacitor of capacitance C here, and I have a load resistor again here is my R. So I am getting my output at this particular point. So this is my final output. Okay, listen carefully. So in this point we have a DC and AC. So we have a AC behavior, fluctuating behavior, and DC behavior means is your positivity. So what's happening here? My capacitor, which will offers infinite resistance for direct current. So how it is? So in the capacitors, when you are sending AC to the capacitor, we have a resistance, it's called capacitive reactance. Capacitive reactance Xc equals to 1 by C omega. 1 by C omega is nothing but it acts as a resistance, right? So here my omega is going to be 0 for DC, for direct current, which means there is no fluctuation. My omega is 0 for the DC. If my omega is 0 now, then your Xc is going to be infinity for DC. So this is infinity for DC. So my capacitors always offers infinite resistance for the direct current, which will permit only the alternating current. So which will permit only AC across it, which will ripple the DC. So the rippled DC I can get here. This will filter out. We are filter out the AC separately and DC separately. So my capacitor, which will not permit any DC current across it, which will filter, which will ripple my DC here. The rippled DC I am getting here. So listen carefully. From this point to this point gets increases. Once increased is going to be this, something like this. So this fluctuation is negligible. This is for only for some nanoseconds. So my final output from here I can get this. So my full wave is completely rectified here, and then further I am getting my filter circuit from here. So my full wave, my alternating current is completely now converted into direct current. This is very important application. So I just stop at this point. If you like this video, share it with your friends and subscribe our channel for the more content. Thanks for watching. We'll meet in the next video. Thank you.